Today, let's talk about exponential functions. Let's start with a definition. If we have a number, say a, and that number is greater than 0, and that number also does not equal 1, then an exponential function would be in the form f of x is equal to a to the x, where a is referred to as the base and x can be any real number. This is the standard form for exponential functions. Now, why can't a be less than 0? Well, that's because if we have f of x is equal to 0 to the power of, say, 2, we're just going to get 0. And same for if a was equal to 1. If a was equal to 1, and we'd have 1 to the power of, say, 5, our answer will still be 1. What if a is a negative number? Well, if a was a negative number, and we had, say, f of x is equal to negative 1 to the 1/2 power, we would get the square root of negative 1. So we avoid negative numbers because we don't want to get any complex values out of the function evaluation. Ideally, we want our solution to be a real number. So now that we've talked about some exponential function no-nos, let's look at the properties of exponential functions. If we have an exponential function in the form a to the x power times a to the y power, where x and y are both real numbers, this would simplify to a to the x plus y power. So we can just add the exponents together. So say we have 2 to the 3rd power times 2 to the 9th power, we would get 2 to the 12th power. If we had, say, a to the x power, and this whole value was raised to the y power, this can be simplified to a to the x times y power. For example, if we had 2 to the 3rd power, and that was all raised to the 2nd power, this would be equal to 2 to the 6th power. Now, what if we had two different numbers? We have a and then times b, and then their product would be raised to the x power. This can be simplified as a to the x power times b to the x power. So we can just distribute that exponent to each of these terms. So if we had 2 times 3, and that was raised to the 2nd power, this would be equal to 2 to the 2nd power times 3 to the 2nd power. Now, what if instead of multiplying, we were dividing? What if we had a divided by b, and that was raised to the x power? In this case, it can be simplified as a to the x power over b to the x power. Right, so if we had 1/2, and that was raised to the 2nd power, we would get 1 to the 2nd power over 2 to the 2nd power. Now, what if we had a to the x power over a to the y power? Same base number and two different real numbers in the exponents. This can be simplified to a to the x minus y power. Right, so if we had 2 to the 5th power over 2 to the 2nd power, this would just be 2 to the 5 minus 2, 3rd power. Next, let's talk about the natural exponential function, where f of x is equal to e to the x power, where e is equal to 2.718 and so on. It's an irrational number called Euler's number, the graph of which looks something like this. This is an important function to know. You'll see it in a lot of exponential functions. And it's interesting too, because at any point the slope of e to the x equals the value of e to the x. So let's say we have our point 0, 1. The slope at this point would equal 1. Also, the area up to any x value, e to the x. Now let's do a couple examples. Let's sketch the graph of f of x is equal to 2 to the x power. We need to find some points. So let's go ahead and plug some values into our x. So first let's plug in 0, and we'd get 2 to the 0 power, which gives us 1. This is our y value for the coordinate, and our x value was 0. So our first point is 0, 1, 0, 1, right here. Let's find the point at x equals 1. So we have f of 1. It gives us 2 to the first power, which is just 2. So there's our next point, 1, 2. So we go over 1, 2. Next, let's set x to -1. So we have f of -1. That gives us 2 to the negative first power, which is equal to 1 over 2 to the first power. And that gives us 1/2. So at x is -1, we go up 1/2. So that's about here. And we'll do -2. We'll find one more point. F of -2, that's 2 to the negative second power, which is 1 over 2 to the second power, which gives us 1 over 4. So at -2, on the x-axis, on the y-axis, we go up 1/4. So that's like down here. Yeah. Now we can keep finding more points, but let's just fill in what we got. The graph for this is going to look something like that. That's the graph for 2 to the x power. Let's also graph f of x is equal to 1/2 all to the x power. We'll do it in a different color so that we can graph it on the same graph and compare. So let's find our point at x is -2. So we have f of -2 gives us 1/2 all raised to the negative second power. And because the exponent's negative, we can flip the inside. That gives us 2 over 1 to the second power, which gives us just 4. So we have our first point, -2 and 4. So at -2, we'll go up 4 right there. Let's do -1. F of -1, 1/2 to the negative first power, gives us 2 over 1 to the first power, and that gives us just 2. So our second point is -1 and 2, right there. At 0, we have f of 0, that's 1/2 to the 0 power. Anything to the 0 power is just going to give us 1. So our next point, 0, 1, 0, 1, matches up with our last one. Let's quickly do x is equal to 1, so f of 1, that gives us 1/2 to the first power, just leaves us with 1/2. So at 1, we're down to 1/2. And then for 2, we have f of 2 equals 1/2 to the second power, and that gives us 1/4. So at 2, we're down to 1/4. And we'll stop there. So here's our line. If I drew these better, you would see that they're almost mirrored in a way. Let's try this one. It's a little harder. So we have f of x is equal to 5 times e to the 1 minus x power minus 4. So let's find our point at x is equal to -1. So we just need to plug in -1 into our x. So we get 5e 1 minus -1 minus 4. This gives us 5e to the second power minus 4. And if we type e squared into the calculator, we'll get 5 times 7.39-ish minus 4, which gives us about 32.9. So our first point will be at -1, 32.9, about here maybe. Then at x is 0, we'll have 5e to the 1 minus 0 minus 4, which is 5e to the first power minus 4, which gives us about 9.6. So our next point is 0, 9.6, about there, I guess. Then at x is 1, we get 5e 1 to the 1 minus 1 power minus 4, which is 5 times e to the 0 power minus 4. E to the 0 power, that's just 1. So we get 5 minus 4, and that's 1. So at 1, we're at 1, getting small. And we could keep filling in values, but I'll just show you what the graph looks like. It's going to be something like... something like this. Imagine a smooth curve. Kind of rough, yeah. Next, let's solve a problem having to do with population growth. So say we have two cities, the population of which grow according to these two exponential functions, where P1 and P2 are the populations in thousands of cities A and B respectively. T is the time in years, and it's a positive number. And when T is 0, that corresponds to the year 2023. When will the populations of the two cities be equal, and what will be their populations? So first, let's set P1 and P2 equal to each other. So we have P1, which is 100 times e to the 0.013 t power. And we'll set that equal to 110 e to the 0.008 t power. And let's make these t's t prime, signifying the time that these two populations are equal. Now let's rearrange this. Let's divide e to the 0.008 t prime on both sides. Cancel that out. And we can divide 100 from this side so that we can put it over on this side. So we're left with e to the 0.013 t prime over e to the 0.008 t prime is equal to 110 over 100. Let's look at this side with the exponents. We see that we have these two numbers being divided. They have the same base. We can use a property. The one where if we have a to the x over a to the y, that can give us a to the x minus y. And we get e to the 0.013 t prime minus 0.008 t prime, and that's equal to 1.1. That's our 110 over 100. So now we can simplify this. We can just subtract the exponents. That gives us e to the 0.005 t prime equals 1.1. Now we can take the natural log on both sides, and that's going to give us 0.005 t prime is equal to the natural log of 1.1. The natural log here just cancels the e out and then brings this exponent into the base. So now we can get t prime by itself, and that gives us natural log 1.1 over 0.005. And if we type that into a calculator, that gives us about 19. So 19 years. So in 19 years, the population of the two cities will be equal. So in 2042. So now let's take this value for t and let's plug it into our original equations. So for P1, let's do P1 of 19. That's going to give us 100 e to the 0.013 times 19. And that's going to give us about 128 thousands, because our population is in thousands. So 128,000, and it's going to be the same for P2, 128 thousands. And here's what the graph for that would look like, where t is on the x-axis. At 19 years, P1 and P2 will be equal. At 19 years and 128,000-ish people. So that's it for this video. We went over properties of exponential functions. We looked at the natural exponent. We went over some examples and graphed them step by step. And then we did one big real-life example. I hope this was informative for you, and thank you for watching.